Okay, what follows is again a short presentation about work, um, potential energy, conservation of energy that's we find in chapters 6 and 7. We begin by defining work, and first of all, work is done by a force. We talk about the work done by a tension, the work done by a weight, work done by friction. Um, Work is done by a force, and one needs to be very careful when answering a question about work, that you know uh, work done by what. The definition of work written here as an integral. The work is equal to the integral from the reference level to some position x of f dot ds, or when the force is constant, it simplifies to f, the displacement, the magnitude of the force, s, the magnitude of the displacement, cosine theta, where theta is the angle between the force and the displacement for a constant force. Or if the force happens to vary with x, then what we want work is the area under the force versus displacement graph. So work, it's a concept you should be familiar with. You used it um, enough last year. You had to calculate work done by a variety of forces. Um, Very important associated with work is this theorem, network kinetic energy theorem. And this says that the net work done on an object is equal to the change in the kinetic energy of that object. Net work equals change in kinetic energy. Uh, the, the, uh, the, the mistake that is often made is um, not using the net work in this equation, but rather using the work done by one of the forces or a couple of the forces. uh, and trying to set that equal to the change in kinetic energy. The theorem says that the network must be equal to the change in kinetic energy. So what do we mean by network? Let's look at this problem here where we have a block on an inclined plane, and we're going to push this block up the inclined plane through a displacement S. So these are the forces that are acting on our block. Very familiar forces. We have a push, a friction, a normal, and of course the weight. What do we mean by the net work done as we push this block through a displacement S? Uh, well, the net work, whatever it is, will be equal to the change in the kinetic energy. Change in kinetic energy, of course, is the final kinetic energy, the kinetic energy at the top minus the initial kinetic energy. The net work. One way of defining network is the work done by the net force. And so to calculate the net force, looking at the free body diagram, we see the net force involves the push, the friction, and the component of the weight. And so we write that the net work is equal to now P minus mg sine theta minus Fk. This is the net force multiplied by the displacement. I know the net force is in the same direction as displacement, so we have a cosine zero term here. So this is one way in which we can calculate the net work. And this theorem says that this net work can be set equal to the change in the kinetic energy. Well, there's another way of calculating the net work. What we can do is calculate the work done by each of the forces and sum them all up. Now, work is a scalar, so when we sum up the works, we're just adding them. Keeping in mind that work can be negative, so we're going to have some positive quantities, some negative quantities. Calculate the work done by each of the forces and add them all up. So this ends up being the work done by the push, which is positive, the work done by the normal force, which is 0, the work done by the weight, which is negative, the work done by the kinetic friction force, which is also negative. We add them all up. That gives us a net work, and we can set then that equal to the change in the kinetic energy. So the network kinetic energy theorem, very important theorem that we use frequently. Um, Somewhat associated with work, but not exactly equal to this, is this idea of potential energy. Potential energy. What does it mean? Well, our textbook defines potential energy as an energy associated with a system configuration, that is, where the system is and what it's interacting with, which is correct, but it's somewhat a vague kind of definition, not a very useful definition. And so I prefer this definition here, that the potential energy is equal to the work done by an external agent in moving an object from the reference level to some position x. And that gives me the potential energy as a function of x. It's the work done, so it can be expressed as this integral. The integral of the external force, the force exerted by the external agent, dot ds. So when we take an object and move the object, the work done by the external agent is whatever is moving the object. Me, I'm the external agent. In this example here, we're taking a block of mass mg. Forces are mg downward. I'm exerting a force of mg upward because this is in equilibrium. And I'm going to move it to some position y from the reference level. That's some arbitrary level at which the potential energy is equal to 0. To some position y. Now, in order to do that, I have to exert a force of mg through a displacement y, and the force is in the same direction as the displacement y. And so the potential energy at that position y is equal to the work done by me in doing so. And clearly the work that I did is equal to mg times y. And so mgy is the work that I did in moving it from the reference level to position y. So the potential energy at position y is equal to mgy. And this is an expression that we are very, very familiar with. Now, in doing this, again, F external, that's the force that I exert, and that is equal to, but opposite to, the force. In this case, the force was the force of gravity, the weight of the object. It was an equal in magnitude, but opposite direction. The force that I exerted, it was equal and opposite to the weight, the conservative force. And so I have to exert a force equal and opposite to the conservative force. Why? Well, to maintain equilibrium as I move it. So that the net force is equal to 0. And so while we write that the potential energy is the work done by the external agent, I can substitute this external agent, the force exerted by the external agent, using this relationship, as negative the force exerted by the conservative force. In doing so and solving for the conservative force, I can write then that the conservative force is equal to negative the derivative of the potential energy function with respect to x. And so this is an important relationship. And what it says is that if you have a graph of potential energy as a function of x, the force is negative the slope of the potential energy graph. Keep that in mind, very important. Here's another potential energy that we're going to encounter. This is the potential energy of a spring. We know that the spring force is a force that is not constant, but in fact, as I compress the spring, or as I stretch the spring, in fact, the force increases linearly. That the spring force is proportional to the displacement, or is equal to k times x. And so from the unstretched position where the spring is right now, x is equal to 0, I'm going to compress this spring, and in doing so I have to do work. The amount of work that I do is equal to, in this case, the area under the force versus displacement graph, which is a triangle. And the area under the triangle is 1/2 kx times x, or 1/2 kx squared. Or if I substitute for the force, the spring force, the force that I have to exert, kx, and take the integral, I get the same thing, 1/2 kx squared. So the potential energy of a spring is 1/2 kx squared. Potential energy. Now, the reason we define this quantity potential energy is to use it in the law of conservation of energy. If there are only conservative forces involved, gravity, weight, and those would likely be the most common forces that we'll encounter in this chapter, we can write that the kinetic energy plus potential energy at some point must be equal to the kinetic energy plus potential energy at any other point. That the energy, kinetic plus potential, is conserved, is constant. Now there are other ways of expressing this law of conservation of energy, but I don't think any of them are as clear as this. I mean, conservation means constancy of energy. And here we're saying is that the energy, K plus U, kinetic plus potential, is the same, is conserved. Kinetic K1 plus U1 is equal to K2 plus U2. Kinetic energy plus potential energy at some time equals kinetic energy plus potential energy at any other time. Now, if there are non-conservative forces, in particular friction, friction is probably the most common non-conservative forces that we will encounter. Kinetic energy plus potential energy is no longer equal to kinetic energy plus potential energy later. In fact, if you stop and think about this, if there is friction, will the kinetic energy and plus potential energy before be greater or less than the energy later? Well, clearly what's going to happen is that some energy will be lost, will be sucked out of the system by friction. And so to make an equation out of this, I'm going to have to add a positive quantity to the later, the right-hand side. I'm going to have to add. Then why is this written as negative, the work done by friction? Why am I subtracting the work done by friction? Well, keep in mind that the work done by friction is inherently a negative quantity. So I'm taking the energy after minus a negative quantity, which means I'm really adding a positive quantity to the right-hand side. Think about this. A conservation of energy with conservative forces and with non-conservative forces. It works.